We've all been there, right? Stuck in line, thinking, there has to be a better way. Well, it turns out there's a whole hidden science dedicated to that exact problem. And today we're going to pull back the curtain and see how the science of queuing, yeah, waiting in line, is actually powering the super smart factories of the future. But to really get how deep this goes, we've got to start with a simple question.
So seriously, what does a high-tech, smart factory buzzing with robots and automated vehicles have in common with a packed waiting room? It sounds like a riddle, but the answer is everything. It's all about how you look at them. See, they're not just a factory and a waiting room. They're both complex systems where you have limited resources and totally unpredictable demand. And here's the cool part. Figuring out how to fix one gives us the blueprint to perfect the other.
And this really breaks down that huge shift we're talking about. On the one hand, you've got this simple, old-school line, first come, first served. Pretty straightforward. But on the other side, you've got the smart factory. And that's a whole different beast. It's dynamic, it's kind of messy, and we're not just counting minutes anymore. Nope. Now we're juggling shared robots, making decisions in real time, and even factoring in things like the human cost of crowding.
And that brings us to our first really big idea here. Because, the cost of waiting, it isn't just about the minutes sticking by. There's this whole other hidden layer, a social cost, that scientists are just now figuring out how to actually measure. So back in 2023, some researchers, Hassan, Millickson, and Perlman, they finally gave this feeling a name, person-time exposure. And it's so simple when you hear it. The idea is that it's not just about how long you wait, it's about who you're stuck waiting with. It's a way to put a real number on the stress and, the sheer annoyance of being stuck in a huge crowd. And what's so cool here is how you can see this idea in action. Okay, a 10-minute wait. If you're all by yourself, the cost is pretty low. No big deal. But that exact same 10 minutes in a room packed with people, it feels way, way worse. That's a high cost. So the whole game for any smart system, whether it's a hospital or a factory, is to find that sweet spot, that safe threshold, to keep that social cost under control.
Okay, so that covers the individual experience. But what happens when you've got a bunch of different players in the mix? Think about it, maybe different companies or different production lines, all needing to use the same fleet of robots. How on earth do you make that fair? And that's a huge question in game theory, something researchers like Liu and Yu were digging into back in 2022. Because let's be real, if everyone just acts in their own self-interest, the whole system just collapses. It grinds to a halt. So you've got to build a system that actually makes people want to work together. And the solution they came up with is basically a cooperative game. Now, don't get thrown by that big term, polymatroid optimization. I know, it sounds intense. But just think of it as a fancy recipe for fairness in 3 simple steps. First, you map out the whole system. Second, you set the rules for how to share everything. And third, and this is the absolute key, you figure out a way to share the costs that's so fair, so stable, that nobody is better off just quitting and going it alone. It's literally math that makes everyone play nice. All right, so we've covered how to manage people and how to get different players to cooperate. But now let's look at the system itself, because this is where things can get, really weird. Sometimes the things we do to improve a system can backfire in the most bizarre ways. So just take a look at this setup. We've got a pretty basic factory network, right? 4 stations, a part makes its way through, and on average it takes about 5 minutes. Not too shabby. But of course the managers are thinking, hey, how can we speed this up? So what do? They add this brand new, super fast shortcut between 2 of the stations. Logically, that should make everything faster, right? Well, no. The average wait time actually jumped to 7 minutes. It got worse. And this isn't just a hypothetical. It's a real thing called Brace's paradox. And researchers like Hillis's team just saw it happen in systems like this in 2024. And this just hammers home a fundamental, kind of mind-bending truth about complex systems. Adding more options can actually make everything worse. You've probably seen this in real life, right? A city adds a new highway to fix traffic, and somehow the traffic gets even worse. It's the exact same idea. That new option creates a new bottleneck nobody saw coming. It just goes to show you can't just blindly throw more resources at a problem. You have to understand the whole system. So, okay, if our own intuition can totally lead us down the wrong path, how in the world do we manage all this complexity? Well, the answer isn't to just try and program a better, rigid solution. It's to build systems that can actually learn and adapt all by themselves.
Here's a good way to think about it. Traditional programming is like giving a robot a very specific, static blueprint. Do this, then this, then this. But if anything changes, a machine goes down, a priority order comes in, that robot is completely lost. Reinforcement learning, or RL, is totally different. It's like telling the robot, here's the goal, and then letting it figure out the best way to get there all on its own, through trial and error. It actually learns as it goes.
So these AI systems use something called a Markov decision process, another big term, but just think of it like a super intelligent GPS for making decisions. At every single choice point, it's looking at the current situation and calculating all the possible future outcomes to find the absolute best path forward. This lets it discover amazing strategies for scheduling and routing. And get this, thanks to really recent breakthroughs, like from Grossoff's team in 2025, we have mathematical proof that these AI systems will find better solutions. We can actually truly trust the decisions the AI makes. So where is all this taking us? We've kind of gone on a journey here, right? We've seen the whole idea of a line evolve from just a simple weight to this incredibly complex dance of machines that learn on the fly. Think about the progression. In the past, it was all about one simple thing. How do we cut down the wait time? Then we got a little smarter and realized the social experience, the feeling of waiting, actually matters. Now we're at the point where we can build systems that manage how whole groups cooperate. And the future, which is pretty much already here, is all about creating queues that are completely autonomous, systems that think for themselves. Which leaves us with one last big question to chew on. As these systems become less like tools and more like intelligent partners, what does the perfect queue of the future even look like? Maybe, just maybe, the perfect line is the one you never even realized you were in. As our world gets smarter at managing flow, the whole concept of waiting might just disappear. I mean, what do you think that world looks like?